Welcome to my presentation, Geometric Gauges, Plain and Simple. In this talk, I hope to give a modern perspective on geometry and what kind of benefits this modern perspective can give you in your own research. So first, I'd like to talk about reflections. That's going to be very basic, and we're going to talk about the geometric properties of reflections that we would like to preserve, and specifically to preserve when we start going to higher and higher numbers of dimensions. And we will rediscover that Clifford or geometric algebras are the natural algebra of Euclidean geometry, but also of other types of geometries. And then I will stress something I call dimension agnostic thinking. And this is a different mindset for doing geometry. And in this mindset, we can solve problems in a lower number of dimensions and then just change the dimensionality of our algebra. And if we did things correctly, then our solutions will still work. And that is a real superpower. And finally, I want to show what geometric gauges can bring us in terms of geometric intuition, but also that it can really solve some theorems in a quite easy way and at least give you a much deeper understanding of these theorems. And that I will do with the Catan-Jordanay theorem and the invariant decomposition theorem. So first we're going to talk a bit about reflections. And we start with reflections in one dimension. So in one dimension, all you have is the line, and you have points on that line. And then I can make shapes, which in this case is just a line segment. And I've highlighted also the head of this shape so that you can see which way it is facing. So if I now reflect this shape in the point A, you see that it ends up on the other side, and the head is now on the other side. But notice that all the points on the line will have been transformed under this reflection, except for the point A itself, which is an invariant, of course, under the reflection in A. Okay, fair enough. Now I add a second reflection in a point B, and then you see that this orange line segment moves again to the other side, is reflected. But now you see that this combination of first a reflection in A and then in B has the net effect of translating our blue shape to this new position, right? Because the head is now again on the same side. So this shape has just been translated along the line. And this means that 2 point reflections make a translation over twice the distance between those points. But how do you know that this scenario really was 1D and not 2D? Or in fact, I animated this in 3D. So that means that this scenario should still work when we go to higher and higher dimensions. So we would like these properties of 1D dimensions, reflections, to remain true when we go to higher numbers of dimensions. So in 2D, we get something new. We can do reflections in lines. And again, that has the effect that this shape is reflected across the line to make this new shape on the other side. And in fact, all the points in the space are reflected. There's only, the only thing that is left invariant is the line itself and the points on this line. But now I can start combining two reflections in 2D, and then we can make something we call bireflections. And these are translations, rotations, or boosts if you go to hyperbolic geometry. And these all have the effect that if I do two reflections in lines of my shape, then I get a translation over twice the distance between those lines. Same thing is true for the rotation. If I first do a reflection in one of these lines and then in the other, the shape ends up over here. But it has been rotated in effect around this intersection point by twice the distance between those lines. The distance being an angle in this case, sorry. And these things we call bireflections. But here's a conundrum. If I gave you the input and the output shape, you could reconstruct the bireflection between them, right? But you could never know which particular two reflections I used to make that bireflection. So if I give you the blue shape and the orange shape, you could figure out that that is a translation over that distance, but you would never know which particular pair of parallel lines that I used. And what that means is that bireflections have a gauge degree of freedom. I'm free to choose my reference angle. And that is important because we can use that to simplify all kinds of computations, as we will see throughout this talk. So there's two honorable mentions among the bireflections that are worth discussing in some more detail. If I have my shape and I reflect it over a line and then again over the same line, it ends up in the same position. And so the identity operator is also a bireflection. I can view identity as two identical reflections because doing the same reflection twice is the same as doing nothing. And in fact, the identity can be seen as an even number of identical reflections. It doesn't have to be just two. And this can be important to carry out certain simplifications, as we will see in a moment. Now, there's another special case, and that is when the two line reflections are orthogonal. So now this blue shape is first reflected across to the upper left corner and then to the lower left corner. But you see that the product of those two reflections, the composition of those two reflections, is the same as a single point reflection in this intersection point. But now I'm going to go one step further and drop the word reflection. So not only are two orthogonal line reflections identical to a point reflection, I'm going to say that a point in 2D is two orthogonal lines. Why? Because it acts the same way. It walks like a duck and it quacks like a duck, so it's a duck. And we'll see an example of why that mindset works right now. So if I consider the product between 2 points, A and B, again, just like in our first slide, but now I look at that product from within 2D instead of 1D like we did on the first slide. So now within 2D, I know that these points can really be seen as two orthogonal lines and that they have a gauge degree of freedom. So I'm free to choose any factorization into two orthogonal lines of each of these points, and that just makes the same point. And now I'm going to do a very particular choice. I'm going to choose this factorization into two orthogonal lines in such a way that one of the lines from A goes through the point B. And for B, I'm going to do the same. I'm going to factorize it such that one of those lines goes through A. And you see that the moment that that happens, I have done the same reflection twice, which is the same as doing nothing. So really that second line from each, one line of each, disappears. And what I'm left with are these two parallel lines. And we have already seen that two parallel line reflections make a translation. So now I have recovered that the product of 2 points in 2D produces a translation. And it's specifically the translation along this line through the points A and B. So this is consistent with what I wanted in my first slide, that when we go to higher numbers of dimensions, it must still be true that the composition of 2 point reflections produces a translation. And so that is still true here, and it is still a translation of twice the distance between these two lines now. So now I can start to formulate a realization of this geometry. And the way we do that is by making first some observations. Firstly, reflections are involuntary, which means that if I do the same reflection R twice, then it should be the same as plus or negative 1. And this goes for point, line, plane, etc. reflections alike in any number of dimensions. A second observation is that in a Clifford algebra or a geometric algebra, the products of orthogonal vectors square to scalars. So if I take the exterior product here of k different vectors, then the resulting quantity, which is called a blade, will always square to a scalar. And I'm working over real Clifford algebras here, so it's going to be a real scalar. And the effect of this exterior product is that I can always represent an exterior product of vectors as just the product of orthogonal vectors. So that is a good sign, because now you can start to see that we can start to represent our point as the intersection of two lines with a blade. And moreover, it is well known that the products of vectors in a Clifford algebra are elements of pin groups being reflection groups. So that means that we can start to embed this geometrical story in Clifford algebras. And this will work if we represent the grade 1 vectors, if we take the grade 1 vectors to be identified with hyperplanes, instead of with arrows pointing at points. Okay? And the way in which we do that is, if I have the equation of a hyperplane in a pseudo-Euclidean space RPQ, then the equation of a hyperplane is in general always such a linear equation, and it is equal to negative b. I take the negative as a convention. And now I can embed this equation of a hyperplane in a Clifford algebra of one dimension larger. So how I do that is by taking the same coefficients of this hyperplane and taking them as the coefficients of the basis vectors of the Clifford algebra. And to represent this coefficient, I add an extra plus b e0, where e0 is the extra basis vector of my 1-up Clifford algebra. And depending on the choice I make for this e0, we get different geometries. So if I choose e0 to square to 1, I get elliptic projective geometric algebra, or PGA. And if I take e0 to square to -1, I get hyperbolic PGA. And finally, if I take e0 to square to 0, I get a Euclidean PGA. Now, some intuition for why e0 squares to 0 makes sense for our normal Euclidean space is that, remember that we are now going to use the vectors to represent hyperplanes. And so each of these basis vectors is also a hyperplane. So if you think about 3D space, you have 3 planes through the origin, and then this e0 represents the extra plane that I need to represent the hyperplane at infinity. And this hyperplane at infinity, you cannot reflect in it and live to tell about it, because you cannot reflect past infinity. And that is why this should be a vector that squares to 0. So then we finally have our algebra of geometry. In 1D, all the elements I have are points, and I can compose 2 points to make a translation. But then when I go to 2D, I get one new extra element, the line, and 2 orthogonal lines make a point. And so now I have rediscovered the point, so everything I already had in 1D is now embedded within 2D. And with the line, I can start to make transformations based on lines as well. When we go to 3D, I again get something new, the plane, but 2 orthogonal planes make a line. And so that means that everything I already knew about lines is now again true within 3D. And with 3 orthogonal planes, I can make a point. So that means everything I knew about points is also again true within 3D. And so if you build up the algebra in this way, you very consistently get a proper encoding of all the different dimensionalities within the same framework. Something interesting to just briefly point out is that because now the points are actually pseudo vectors in this space, so they are the intersection of multiple planes, that means that points are not just some boring zero-dimensional quantity, but rather they have an internal structure and they have a local spin gauge group depending on your signature. And so, for example, this point here in 3D as the intersection of three orthogonal planes, those three planes are not uniquely determined. So I have a spin 3 degree of freedom there. And that means an SU2 essentially. So this is also very interesting for the physicists in the room. All right, and then I would like to point out the dimension agnostic thinking that we can do because of this algebra of geometry that we have now built. Now, if you are interested in following along on your own computer, I recommend that you scan this QR code, and that will take you to the source code of the following example. So I have the thin lens example here from physics, where I have a lens, and this lens has a center point and a focal point, which are important. And I want to know where does this point get mapped through this lens. And then your physics teacher will have told you that the rules are that any light ray that goes through the center of this lens passes through unchanged, and that any light ray going through a focal point will leave the lens orthogonally. And so that is what I have shown here, and the code to do that are just these couple of lines. So I construct the lens in 2D, by the way, this is all in 2D. I construct the lens as a line, E1. I have the center of the point, which is the center of the lens, which is the dual of the line at infinity. So that's the origin, that's this point here. And then I have my focal point, which is again the dual of some line. Then I have the object to mention, to image, which is again the dual of some line. So that's a point, that's this point here. And then I can start to really do the geometrical construction that your teacher will have hopefully told you about. So I take my world that I want to image, I join that with the center of the lens, that gives me this line here. So that's the first piece of the puzzle. Then I construct the other line through the focal point, and then I intersect that with the lens, and that gives me this point here. So then we are here in the third line. Then the next line is a bit more technical, but that one gives me a way to construct this line that leaves the lens orthogonally. And then finally, I take the intersection of those two lines with the exterior product, and that gives me the image point. Okay, so far so good. So you can already see that the construction is very geometrical because each of these binary operators has a very geometrical meaning. I'm either joining some points or I'm intersecting some lines. But now I can change the dimension from 2 to 3, and the exact same code still works, right? Because of the way I defined all these quantities, because E1 is now suddenly a plane, my lens has become a plane. But all these points, I defined them as the dual of the vectors, so they remain points even when I change the dimension of the algebra. But now we can go a step further, and that is to change perhaps what I would like to image. What if I don't want to image a point, but I would like to image a line? So all I do is I change the thing to image to be a line, and now you see that this lens has the effect of mapping this line to a new line. But it doesn't even stop there. I can also change the type of the lens. So what if I want to use a cylindrical lens instead of a spherical lens? Well, to do that, I have to change the properties of the lens so that the center of the lens has become a line and the focal point has become a line. And now this lens has the effect of mapping points to lines. And this is the type of lens that I use to correct for my horrible astigmatism. And so you see that with these kinds of, this way of thinking, my solution that I have coded is not just agnostic to the dimension of the algebra, which I can change at will, but also the dimension of the inputs. But the fundamental code for the algorithms didn't change at all. And this is a real superpower. And this is what I would like to stress with this dimension agnostic thinking, that if you formulate your problems correctly in this plane-based mindset, then your solutions will keep on working independent of the dimension of the input, or indeed the algebra. So I hope to have now shown you already some convincing arguments for why this plane-based mindset is very powerful. But I'd like to go one step further and show you how these geometric gauges can supercharge your intuition. So the geometric gauges are really the mechanism behind all the products between geometric algebras, geometric elements like points, lines, planes, and also behind the projection formulas, the conjugation of the group, and all of these can be explained with the geometric gauges. But I would like to now only go into detail for the Cartan-Giordani theorem and the invariant decomposition theorem. So what is Cartan-Giordani? This is the statement that every orthogonal transformation in an n-dimensional embedding space is composed from at most n reflections. And what I show in this animation is if I take this square and I reflect that in 4 different lines, it ends up over here. But really we have these gauge degrees of freedom in every intersection between 2 of these lines. And you can use that to make 2 of these lines identical, and it just disappears. And what's left is just 2 reflections, which makes a rotation around that new intersection point. And I think if I hadn't told you about geometric gauges, then it would have been quite complicated to predict what the net transformation would be. And you wouldn't have easily guessed this point, perhaps. But the geometric gauges allow you to just very geometrically reason about what the invariants are. And even more interesting is the invariant decomposition theorem. So what I show in this image is if I reflect in this one green line, then this vector field is meant to show how much every point has to move. So if you are a point all the way out here, you have to move all the way across to your final destination. If you're a bit closer to this reflection, you only have to go out there somewhere. And if you are near this line, you hardly have to move at all. And the points on the line really don't move, and they are invariants of this reflection. And not just the points on that line are invariant, but also the line as a whole. But then if I do 2 reflections, now all the points start to rotate. And so there are no invariant points left except for one, which is the intersection point of these 2 reflections. And there is actually one other invariant quantity, and that is the plane as a whole, which is not unimportant if you want to think in a geometric, in a dimension agnostic way. But so all the points now move except for one. And so you might think that if you do 3 reflections in the plane, then there can be no invariant anymore, right? And so if you look at this image, it does seem to be that there is a bit of an invariant, right? Because all the points all the way out here have to really move across, but the points that are around this line, there seems to be some kind of imaginary line here, and those points don't really seem to have to move across, but there is still a flow into the upper left direction in this entire picture. So these points here are not invariant, they are all flowing towards the upper left. But at the same time, there is kind of this line here, which does seem to be an invariant. This line. And so indeed, under these 3 reflections, there is an invariant line. this particular purple line. Now, how could you have found that invariant line? The answer wouldn't surprise you anymore by this point. The answer is again the geometric gauges, because I am free to factorize this particular bireflection any way I like. So I will rotate that and choose this particular factorization of the transformation instead. And now you see that I clearly have two parallel line reflections, so that makes a translation, and I have one reflection in this purple line. And so that explains why there seems to be this flow towards the upper left corner. And these two transformations in fact commute. So I could first do the translation and then the reflection, or the other way around. And now we can also see which quantities are the invariants of this transformation. It is this line here, but also the intersection point of those two parallel lines at infinity is an invariant of this transformation. Now this theorem basically reads as follows. Every two-dimensional tri-reflection can be decomposed as a translation along a line followed or preceded by a reflection in the same line. But more famous is the three-dimensional analog of the same statement, and that is known as Mossy-Schall theorem. So that concerns screw motions, which are the most general rigid body motion you can do in 3 dimensions. And it states that every three-dimensional rigid body motion can be decomposed into a translation along a line, followed or preceded by a rotation around the same line. And you see that in this figure. You can decompose it in such a way that if I first do a rotation in this one line, then all that's left is this one-dimensional subspace of the axis of rotation. And what can I still do within that subspace? Well, point reflections. So I can still do 2 point reflections in that line, or within the subspace of that line. That gives me a translation, which in terms of planes looks like this again. So that's 4 different reflections in planes. And again, the statement is that this can always be done, and you can always decompose it into a translation along a line followed or preceded by a rotation around the same line. But we can start to abstract the language of this theorem a bit now to see if that gets us something interesting. So every three-dimensional rigid body motion, we have a new word for that now. We would call that a quad reflection. And followed or preceded, there's also a better technical term for that, that is commuting. And finally, we have rotation and translation. We would now call those bireflections. So every quad reflection can be decomposed into commuting bireflections. And now the generalization of this statement kind of presents itself, right? Because why stop at a quad reflection? What happens if I do 6 reflections? And that is the invariant decomposition theorem. And that theorem states that a product U of n reflections, which is an element of a pin group, can be decomposed into exactly ceil n over 2 simple commuting factors. And these are k bireflections, and for odd n, 1 extra reflection. That's quite a mouthful, but I have just shown you the 3D and the 3 reflection and the 4 reflection versions of this. And this is just the generalization of that to arbitrary pin elements. So given such a U, how do you actually perform this decomposition? If it is an odd element of a pin group, then to find the first reflection, the reflection that ends up being an invariant of the transformation, is simply taking the grade 1 part of that element U, and then you can get the remainder simply by dividing out essentially this single reflection from U, and what you are left with is R, which is a 2K reflection. And now that single reflection and the 2K reflection commute. So that's very nice. We have found our first invariant quantity. And now what we are left with is this 2k reflection R. Now to decompose that into commuting by reflections is a lot trickier. And unfortunately, I do not have time to talk about that now in the time of this talk. But if you are interested, then please scan this QR code to be taken to our paper, or directly Google for this paper. And in the paper, we go into all the details of how you would actually perform this decomposition for a given element of a pin group. Something interesting to note, though, for the topic of this mini symposium is that every bireflection is now going to be of the form alpha I plus beta I times bi, where alpha and beta are just real coefficients, usually a cosine or a sine or the hyperbolic analogues thereof. And this bi has the property that it squares to a real number, and you can take that to be either +1, -1, or 0. So in fact, this gives you a very natural way to make a very rich variety of multi-complex like number systems, where all the complex units will be mutually commuting. And to show you that we did really do a lot of work in this paper, here's the cheat sheet from the paper, which compiles all the most important results, including the invariant decomposition. It's given both on the level of the Lie algebra and of the Lie group. And I would just quickly like to mention that this plane-based mindset that I've been talking about in this talk doesn't just work for orthogonal and Euclidean groups, but it also works for the conformal transformations. And so that brings me to the closing remarks of this presentation. If you scan this QR code, it will take you to the slide set, so that you can look through these animations again if you want. I would also like to recommend everybody to check out bivector.net, which is a website where you will find a lot more information on projective geometric algebra, conformal geometric algebra, and geometric algebras as a whole. And we also have a Discord server there, where you will find a very active community of more than 1,700 people by now who are interested in geometric algebra and its applications. So if that is something for you, please check out bivector.net. But I would like to close this presentation with a quote by Michel Schaal. It's a quote from one of his works in 1875. And I would just like to end on this because it already illustrates that Michel Schaal was already thinking in exactly the direction that I presented here, but that he was already being very careful in proposing this to his colleagues, because the notion that vectors could also be hyperplanes, apparently from the way he phrases it, was already a bit controversial. So what he said was, the application of the same ideas of duality can be extended to mechanics. Indeed, the primitive element of bodies to which the first principles of this science are applied is, as in ancient geometry, the mathematical point. Are we not permitted to think now that by taking the plane for the basic element and no longer the point, we shall be led to other doctrines, making, as it were, a new science? Thank you for your attention.